Hello and welcome to another video. In this video we're going to be working on maximum number of points with cost. And in this one you have a matrix, and starting with 0 points you want to maximize the number of points you can get from the matrix. And to get points you pick a cell in each row, but then when you go down you get that number of points, but you also lose points based on how far apart the columns are. So for every distance 1 the columns are apart, you will lose 1 point. So return the maximum number of points you can achieve, and then they show you what absolute values and so on. So here, you're going to get 3 points here. Then because these are 1 column apart, you will only get 4 points here. And then here, these are 1 column apart, so you'll only get 2. So you're going to get 9. And that's the best. And then in this one, you're going to get 5, you're going to get 3 because they're the same, and you're going to get 3 because these are 1 column apart. So you get 11. That's basically it. Now, people ask like, what algorithm do you pick and things like that. So first thing you want to do, look at the constraints. And you can see that m by n is 10 to the 5th. So that means that this whole matrix takes 10 to the 5th to traverse. So, and this is also going to be good for if you're doing like HackerRank assessments or any kind of that stuff, because they give you constraints. Obviously for live interviews this is as applicable, but for LeetCode in particular, and for any kind of OAs that you do that are just like technical assessments, it's going to be good. So you know for sure that you can have a solution that's n log n or better, where n is this whole matrix. So a really straightforward solution that you can come up with, because you're basically picking a column in each of these, is just like, okay, well, if I'm on some column, like how do I decide what to pick? Like let's say I start here. Which one do I want to go to next? So you can make a really easy DP function that's like, given a column, let's take its value, and then let's just iterate through every single one below it, and let's recurse to those, right? So given this, we'll recurse here, 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 and then also given this, we'll recurse here, here, here. And so basically that is going to be, if m is the rows, it's going to be m by n, and then for every row we're also recursing to every column, so it's going to be m by n squared, and that's not going to pass. So you need something that like traverses this matrix in linear time, or some n log n kind of thing. But for n log n, you're usually looking at like a binary search or something like that, and here like there is no pattern in the matrix, they're not sorted or anything, so you can't really do that. So you're basically looking for a DP solution where ideally once you're at a cell you can figure out like which one to go to next in O of 1. And it's pretty hard to come up with, to be honest. But the main thing to recognize is, let's look at an example here. So here we have this example matrix. So yeah, the problem is you can't just be like, let me start here and let me go to all of them, and then let me start here and go to all of them, and so on. That's not going to work. So ideally, given a cell, you want to know like what's the best one to come to this cell from, or given a cell, what's the best one to go down to, so one or the other. And the main thing to notice here is you can come down to a cell, and this is pretty hard to notice, from either the left or the right or straight above. Now, let's say we're at this cell, or actually this cell, and we're considering every cell we can come down to this cell from that's either right above it or to the right, for example. So all of these, or not all of these, but all of these. Let's just pretend, actually let's do this. Let's say we're coming down here, and we can come down to this from all of these. Let's just only focus on the right side or the one above. Well, if we know the best one here, right, like the best one here is going to be this 8 minus 2. Then when we go and try this cell next, like if we know for sure the best one to come to this one from the right or above is this, when we go to the next one, all of these values are exactly the same, except they're just minus 1. So if I know the best cell to come here from, which is going to have a value of 6, when I come to this cell from any one of these, it's going to be the same thing. The maximum, the best cell from all of those will stay the same, except now that will lose 1 point, right? So it'll be 5. And you can do the same thing for the left, right? So if we come down to this cell from any one of these, the best cell here is going to be this one with a value of 3. Then when we say, okay, what if we come to here from the left, the the best cell will, like all of those will still be the same, right? Like out of all of these, the best cell is still the same. It just loses 1 point. And then the only thing you have to check as well is the one above. So basically we can summarize this in given cell ij, or yeah, like with some coordinates, given a cell, the best cell, or what are the things you have to compare, I guess. So the best cell to come to this cell 2 is the maximum of best cell for its left neighbor minus 1, right? Because if we were here and we came here from all these cells, then here, if we use all those cells, it's going to be minus 1 because all of these cells are one farther apart now. Or value right above it. So for 5, if the best cell had a value of 3, then for this, we can say, okay, let's take that value of 3, subtract 1, that's 2, or right above it, or this same thing, but now for its right neighbor, right? So this best cell for its right neighbor. And we can do these left and right neighbors just by passing horizontally. So to get all the left neighbors, like if we're checking, okay, for this, if we wanted the left neighbors of the cells to the left, we can just traverse the row left to right. And then if we want the best neighbors for the cell to the right, we can just traverse right to left. So for every single row, we will do a left traversal to get the best cell to come from the left, then a right traversal to get the best cell coming from the right, and it's just going to be the best one of those two. So let's kind of walk through how that's going to work. So maybe let's move this over here, and let's just make a copy of this matrix. Okay, and let's just delete all these values, I guess. Yeah. Okay, so for the first row, it's going to be the same, right? Because we just start the first row. You don't come here for anything. Okay. Now for the second row, so we'll have a little pointer. So we're going to keep track of the best, the best value on the left, and it's going to start at 0. So the best value to come to this cell from the left, and we're going to also include the cell above in the calculation for that. So we're going to include the left and the cell above. So for this, the left is 0 and the cell above is 5. So the best value is 5. So it's going to be 5 plus this cell's value, which is 14. And then we're going to update the left, because notice that this cell's left is all of these values. So the new left is also going to include the cell above the current cell we're at. So now this left will be 5. Then we're going to go to the next guy and we're going to say, okay, well, we can either take the best left value we have, which is 5, minus 1, right? Because remember, as we traverse farther and farther from the left, our old left value will lose 1 point. So the best left value is 4, and the value above is 4. So it's the same, so we can just say 4 is the best, and then we will say this is 5, and we have to update this value, right? So this value is now 4. Okay. And then we keep going. So here, the best value on the left is 4 minus 1, which is 3, and the value above it is 1. So 3 or 1, 3 is better, plus 5 is 8. And we update our left to be 3. Then we go over here, and the best value on the left is 3 minus 1, so 2, or this value, which is 8, so we have a total of 10. And then we're done with the left, so we don't need to record this anymore because we're done going left to right. Now we're going to go the other way, right to left, for the same cell. And the right value will start at 0. And so the best value will either be 0, or the one above, or yeah, that's it. 0 or the one above, or its previous value, right? Because the left calculation might be better. For the left, we didn't have to check if the right calculation was better because we didn't do it yet. So as long as the left gave us a positive number, that was always just good. But for the right, the left one that we have here might be better. So the one above is 8. and we have a value of 10, so it's going to be the same thing, right? So it's not going to be the right. We're going to want to take the one above, and then that'll give us our max. And now the new right value is 8 because the one above is 8. So this retains its value. Now we come over here, and so the right is 8 minus 1 because we're further away, right? Like this was the right value, we're further away. Every time we go left, we're one further away. So this is 7, or 1, or its old value. So it's going to be 7 or 1 plus this, or this old value. So 7 plus this is obviously the best, so that will be 12. And the right value that we're going to store here is 7, because the right values we had were 7 or 1. Then we're going to traverse here. So its old right value is 7 minus 1, which is 6. We can even update it. The one above is 4. So it's either going to be 6 plus this or its old value. So 6 plus this is better. That gives us a 7. And the best right value is 6. Then we keep going. So the right value now is 5 because we're one further away, or the one above, same thing. So it's either going to be 5 plus 9 or its old value, which is the same. Okay, so we're done with that. And then we basically just keep doing this. So I'll do one more row. And then that's how you get to the bottom. Or maybe, I guess I could do the whole thing. We can just speed it up. So let's do this. And now we're on this row, and let's make it this. Okay. So the left is 0. The one above is 9. Actually, sorry. So the value that you use for the one above is not the value in the matrix. It's actually the value over here. So in this case, so actually we don't need this matrix. We still do need this matrix to reference the actual cell value, but actually we're basically traversing, like if we're here, the one above is actually here because we can get here from here. And this value is 14, not 9. So this would be, the one above would be 14 plus 2, 16. Okay, and the left value that we store will be 14. And then once we get to the next row, it'll be minus 1, so 13. Whoops. Then we go over here. So this value is a 1. The one above is 7, and the left is 13, so 13 is better. So it'll be 13 plus 1, which will be 14. And maybe I miscalculated something, but hopefully this keeps making sense. Now this left gets decreased by 1 as we go to the next one. Okay, so it's either going to be 12 or 12, which is the same. So 12 plus this value, which is 21. And this 12 gets decreased to 11. And then here, the one above is 10 or 11, so 11's better. And then the value itself is 16. Okay, and now we're gonna go right. I'm not gonna keep changing the pointer. So right now we have 0, then we have 10 plus the value, which is 10 plus 5, so that's worse, and the right is 10, and then we subtract 1 once we get to the next number. So 12 or 9, 12 is better, so 12 plus 9 is 21, and then 12 goes down to 11. And then 11 or 7, 11's better, so or its old value, which the old value is the best, looks like. How did I get 14 here, actually? Yeah, looking at this, I think this is wrong, maybe? Oh, no, never mind, because we're not using this value. Yeah, so that's right. Yeah, so it's 11. Yeah, 11 plus 1, which is 12, but this old value is better, and so 11 goes to 10. Hopefully I didn't screw any of that up. And then 10 plus 2, or the one above. So the one above is better, so this stays the same. Okay. And then finally the last row. So left equals 0. Yeah, you want to use this grid as the values above, not this grid. The only values you want to use this grid for is just the current value of the cell that we don't have. In fact, we can even copy this grid, and then we don't need this grid at all. So we can just say like this value is like 5, 5, 6, 6, and then we basically never have to reference this old grid anymore. Okay, so last one, left is 0. The one above is 16, so obviously 16 is better. 16, and the total value is now 21. and the left is 16, so we're going to subtract 1 as we go to the right. So 15 or 14, 15 is better, 20, and then we subtract 1. Yeah, like that might even be easier. Just copy the whole matrix, at least for the visualization. And then the one above, or 14, the one above is better. So 27, and now this turns into a 21, and then we subtract 1. Whoops. And then, whoops. Okay, can I get it? Okay, and then this one, 20 or 16, 20, 26. And now finally, last part. So, so 16 or its current value. Well, I guess, yeah, so I guess that's why we did need this other matrix. So we did need these other matrix because we needed to know the original values here, which we don't. But that's kind of the idea. You do the same thing for the right and you just get the maximum. So hopefully that makes sense. You need the other matrix because you need these original values, and now we don't have them to compare. But yeah, basically the right, you do the same thing and then you get your answer. So once you fill out this whole grid, you just check what's the maximum value of the bottom row. And the other thing we're going to do is since for every row, we're only referring to the row above it, we're only going to store 2 rows in our result. So we'll have like a previous row, and then we'll have the current row we're working on. And once we fill out our current row, that row will be our previous row, and then we'll have another row we're working on, and so on. So we're only going to store 2 rows for more space. Okay, so let's code that. So first thing we need to do is we need to make a copy of the first row. So we'll call that previous row, and let's get the rows and columns. Okay, and then let's make the row. So we can say int previous row. It's going to be an array. It's going to be new int array with a length of columns, and then we can fill that out. So previous row at I will be points at I or points at 0 at I. So that's the first row. Now we need to have the for loop that fills out every other row. So for int I equals 1, I is less than rows. Okay, so for each row, we're gonna first go left to right, then we'll go right to left. So, and we're gonna keep track of this like left variable. So I'll make that equal to 0. Then we're gonna say for int j equals 0, j is less than columns. And we're also gonna make a new array every time we go to a new row. So cur row, there we go, okay. So yeah, so first we figure out what's our new left value. So left is going to be the maximum of the old left minus 1, right? Because every time you go right, you subtract 1, or the value right above the current place we're at. And the value right above the current place we're at is not this point, it's the previous row right above this column. So previous row at j. Okay, and then we just store this in our current row. So current row j equals left plus the value from the points. That's the only thing we need the points for, is what was the value in there. So this is ij. And we don't need to maximize for the left because originally this is just 0. So okay, so then we can do the exact same thing, but we're gonna go right to left. We don't need to remake the thing. And this is all the same. So now this is right minus 1. And now we actually do need to maximize it because this can have a value now. So okay. And finally at the very end we can just say current row equals, or sorry, previous row equals current row. So we're just reusing these 2 rows. And then at the very end all we have to do is just get the maximum of the current row. So we can just say like int result equals 0 and loop through the current row. I can copy this. And result equals, or the previous row, j. And return it. You can also use a stream, I guess, if you want to. All right. And hopefully you didn't make any mistakes. Yeah, we did. 3. Okay, so let's double check everything. Okay, previous row. So this is fine. Then we're looping. Okay, this is fine. Left, math max, previous row j, that's fine. Left plus points ij, that's fine. So right -1. Yeah, that's fine actually. Current row j equals current row j. So this is wrong. This is right. Okay, let's see if that's it. Hopefully. Nope. Oh, we need a long. That's what it is. Okay. So we can just make all these things long, I guess. Yeah. Yeah, so whenever you see these like huge numbers, it's usually just you use an int instead of a long. Okay, we can use long everywhere to keep it simple. Okay. And there we go. Okay, so this one is m by n, and so we used one row, so that's like O of n, where n is the number of columns. Can you optimize it? No, I don't think you can use a column or something, but this is fine. But yeah, definitely I would say not a medium problem. I'd say this is definitely closer to a hard problem because it's hard to come up with all this stuff. And all the space optimized bottom-up DP is obviously harder. But hopefully, I think it's easier to code this way. Like this is one of the rare cases where bottom-up DP I feel like is easier because we have the recurrence relation that's kind of easy to see and we can just build it row by row. But yeah, hopefully this is helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.